Today let's welcome to this series of lectures in marine hydrodynamics. Today I will give a brief review of all what we have been studied till now, because we started with basic flow description, then we want to discuss about the flow characteristics, basically assuming that whether the flow is inviscid, incompressible, and then we talk about vorticity vector. After vorticity vector we talked about irrotational motion, then we have talked about viscous fluid, inviscid, non-viscous fluid, the importance of there are several differences between the viscous and non-viscous fluid, various characteristics of the inviscid flow, and then we have talked about the conservation equations. Basically our emphasis was on conservation of mass and conservation of momentum. Conservation of mass gives us the continuity equation, and which says that total mass is conserved. On the other hand, we have talked to Euler's equation of motion, where we have talked, which is based on the law of conservation of momentum, basically the Newton's laws of motion, second law of motion. Then afterwards we have talked about, we have again assuming that fluid is a conservative field, we are in the gravitational field is conservative, and we have talked about the Bernoulli's equation. And again we have seen when in case of when the motion is steady, we have seen that the gravitational head plus pressure head plus the velocity head is a constant when the motion is steady. Then we have talked about potential flow. From potential flow, because under the assumption of fluid is inviscid, fluid is incompressible and irrotational, we have found that the existence of velocity potential phi such that q is equal to grad phi, and in the process phi satisfies Laplace equation as which is obtained from the continuity equation. In a similar way, we have talked about the equation of motion from the Euler's equation of motion, which is suitable for inviscid flow. We have derived the Bernoulli's equation of motion. Then we have talked about streamlines, stream function. In case of streamlines, we have seen that the streamline, when the streamline psi is equal to the stream function psi is equal to constant, that gives us the streamlines, and that there is no flow across a streamline, and that has given us the idea about streamline body. So in the process, for benefit of flow description, particularly most of the marine bodies or aerodynamical bodies are assumed to be streamline bodies. So because that will help us, it will reduce, because as we have told that along a streamline there is no flow across a streamline. So when the body is considered streamline, that will be helpful in the design, and also the flow will not be disturbed, and there will be smooth movement of the object when it is moving in the fluid. So in the process we have, because of this reason, many are the aerodynamical bodies or hydrodynamical bodies in water, they are considered as streamline bodies. Then, knowing very well about the velocity potential and the stream function, we have moved to discuss the relation between them. That has given us about the relation between the velocity potential and the stream function, and that is the Cauchy-Riemann equation. That equation we have already seen that how it is. This is given phi x is equal to psi y, and then phi y is equal to minus psi x. So this was the Cauchy-Riemann equation. which are the Cauchy-Riemann equation. Here phi is the velocity potential, and we have psi the stream function. And in both the cases, both phi and psi, they satisfy the, for irrotational motion, phi and psi satisfy the Laplace equation. And we have seen that when the flow, the continuity equation has given us very good understanding about the characteristics of the fluid. Again we have talked about, because in incompressible, most of the flow related to the marine environment, we always assume that density is constant, or d rho by dt is 0, total material derivative is 0. The process for measure analysis we have used as if the flow is fluid is of homogeneous density, or it in some, or in general we have taken d rho by dt is 0. Then in the process we have divergent of q is 0 for a incompressible fluid we have taken. And then as we have seen that both Laplace equation is satisfied in both the cases of the velocity potential as well as the stream function. Then we have in the process we have seen that the characteristics of Laplace equation is borrowed very well to analyze a large class of problem under in the flow regime of incompressible, assuming that the fluid is incompressible and the flow is irrotational. So in the process, because when we look at Laplace equation, the only disturbances, only singularity that comes on the boundary as a result, but there is no flow singularity. There is, because Laplace equation is analytic, the function is a harmonic function, both phi and psi will be harmonic when you assume the flow is irrotational and the fluid is incompressible. So that is one of the benefit, but it has led to other problems. So since although we are solving Laplace equation in both the cases, but still the problem remains, the difficulty remains, because of the various types of flow we introduce, and the various types of flow is introduced by means of what? By means of the boundary. We introduce certain object into the flow or maybe the boundary, and those objects in the flow or the boundary, that brings a boundary surface, and that makes the flow complicated. Like we have seen several examples, whether we have seen the flow in an open channel, we have looked into the flow past a aerofoil or a hydrofoil, or flow past a cylinder, and even if you have seen several cases of flow like sources, sinks, combination of certain uniform flow in the presence of a source or sink, even if we have talked about vortices. So all these things, and again we have talked about conformal mapping. Before going to conformal mapping, let me highlight why conformal mapping has come, because we have seen that the velocity potential phi as well as the stream function psi, they both satisfy the Laplace equation and the Cauchy-Riemann equation. Then from the theory of complex analysis, we understood that we can always define a complex velocity potential W, because phi and psi satisfy the Cauchy-Riemann equation. Then we have seen that we have introduced W, and that we call the complex velocity potential, so that it becomes, so we can express this in terms of a analytic function. So in together, and this was only possible when the flow was two-dimensional in nature, because W is a function of a z, and W is equal to Wz, where z is equal to x plus iy. So major flow has been analyzed, several flows has been analyzed under the assumption that z is equal to x plus iy. So that means we have taken as if the flow is two-dimensional in nature. Another characteristics, the fluid domain is assumed to be two-dimensional in nature, and large number of problems have been analyzed based on this assumption. Then we have seen that how, while talking about, we have started with very simple flows. We started with a uniform flow, then we have talked about sources, sinks, doublets, then we have talked about vortex, we have talked about uniform flow, started with a uniform flow, then we have gone to various kinds of other simple flows like flow by introducing several complex velocity potential. We have analyzed simple flows and we have seen the cross combination of these flows. One of the advantages of this simple flows is that some of the flows may not in principle gives any physical realization of the flow, but when these flows have been combined together, 2 or 3 flows have combined together, that has given us a very flow pattern which are of practical importance. Like we have seen when we have analyzed the uniform flow past a cylinder, there are 2 things we have seen, that one flow is a uniform flow in the horizontal direction, the other is just by circle theorem we have added. If you look at the doublet, in the case of a doublet we have taken, in the case of a doublet we have taken W is equal to mu by Z, and this has come from basically combining 2 sources with suitable arrangement of a source and a. Then we have gone to several flow characteristics. We have talked about stagnation point, stagnation flow, we have talked about cavity formation, cavitation theory, and then we have, when we have come to conformal mapping, it has simplified some of our analysis in the conformal mapping. It has simplified most of our analysis because we have brought in a complex variable Z, and we have taken another variable eta, zeta. There are 2 planes we have talked here, Z plane and zeta plane, and some of the most important conformal mapping are the Joukowski transformation. Then we have talked about Schwarz-Christoffel transformation. We have Joukowski transformation, we have Schwarz-Christoffel transformation. These are very 2 important transformations which we have talked about, and we have seen the application of this transformation in analyzing several types of flows. And then another characteristics which comes across is the singularity in the flow, because we have, as I said, that we always look into, when you look at a analytic, particularly look at Laplace equation, we always look into the flow inside the boundary. There is no disturbances, but inside the domain there is no disturbances, but always the disturbance or the changes in the flow characteristics comes because of the nature of the boundary. There are several types of boundary we have seen. There are, if the boundary is very smooth, then the flow pattern is very smooth, but the problem has come when we have the boundary is not very smooth, like we have seen in the case of when a flow past a wedge, or when we have seen in open channel flow when there is a sharp change in the surface of the boundary. Again, I will talk about when we have analyzed the flow in the presence of sources, sinks or doublets. This, because we have brought in singularity in the flow pattern, like we have seen in the case of a vortex, we have seen near the origin r is equal to 0, the flow is singular, but beyond r is equal to 0, the flow is regular. In a similar manner, we have seen some of the other application, like when we have looked into some of the other applications like vortex motion. In this case also we have seen how we can combine a vortex, the whirlpool motion of a whirlpool, or even if when we have a vortex and a source combined together, the kind of flow it has given. Initially when the two flows are quite separate, but you combine the two flows, which has given a very different type of flows in a similar manner. So after this two-dimensional flow, because we have seen that here that large number of flow has been characterized by this two-dimensional flow, and then the two things, the velocity potential and the stream function psi together, often problems we have seen that often problems it has been easy to analyze, to understand the flow characteristics without even if knowing about the details about the velocity potential phi. In many situations the flow characteristics we have obtained just by always obtaining psi, basically the stream function, and assuming that psi is equal to constant, because that has given us the streamline and that has given the flow characteristics. So in fact most of the problems we have done that. Again when we have gone to this, the case of a, the last few classes we have already seen that how the case of S, the rather I will say about when we have gone to the applied the Joukowski transformation to the hydrofoil or aerofoil theory, aerofoil or flow past a circular cylinder, uniform flow past a circular cylinder or uniform flow past an elliptic cylinder. We have seen how complex was the algebra, but it has given nice transformations were helpful in obtaining very nice form of the solutions. Again we have seen that very nice form of solution has been obtained by the just the application of Schwarz-Christoffel transformation. So overall we have seen that there are large number of problems which has been analyzed just under the assumption of that motion is two-dimensional in nature, but there are, however, there is a limitation and constraint. Almost all flow it cannot be analyzed under the basic assumption of the two-dimensional, under the assumption of the flow problem is in two-dimensional nature, although there is a large number of problems we have analyzed, like the flow past a sphere. The flow past a sphere cannot be analyzed by using the two-dimensional theory. One has to take the recourse of the three-dimensional theory. However, because of the complexity of the nature of the, because here one has to go to the spherical coordinate system, and in the spherical coordinate system one has to, then the problem will be more complex in nature. So because of that, in this course we are not going to the three-dimensional problems in general. In fact, and we are avoiding this part of the analysis. Maybe in some other course three-dimensional flow patterns will be, but though there are specific problems which can be analyzed, and that is because of the complexity of the nature of the problem. The moment you have increasing the another variable, because here we are dealing with the two variable x and y variable, assuming that the flow is two-dimensional in nature, but the moment we add one more variable, that is the z variable, then it becomes more complex to analyze the problem, and in the process the simple analysis what we are able to do just in the two variable will not able to do. Even if we have seen the problems, certain problems we have analyzed assuming the not only in the Cartesian coordinate but also in the cylindrical polar coordinate, assuming that it is symmetric about the in the theta direction. So in the process we have brought down the problem to again in a problem of the polar coordinate, and we have cylindrical in the polar coordinate. We have again the only reformulated the problem in the radial direction, and we are able to handle it easily. All these problems whatever we have discussed till now has several applications, and all these were possible because we had in most of the problem we have assumed that the flow is of potential type. That means flow is irrotational, fluid is incompressible. And in fact, another important result which has given us insight the limitation about the viscous flow, that is the D'Alembert's paradox. When we calculated the uniform flow past a cylinder, then we have seen that the total force that is acting on the cylinder is 0, and that has given us the paradox, the well-known paradox, which is the D'Alembert's paradox. And that again, when we have we have added to this flow pattern, introduced a presence of rather we have introduced a flow past a cylinder in the presence of a circulation. Then we have seen of strength K, we have seen that provides us there is a lift force which has been developed, and that gives us idea that in the presence of circulation, there in the flow a lift force which is originated in the flow pattern. On the other hand, we have seen there is a lift and drag force, both were becoming 0 in the case of flow past a cylinder. That is what the D'Alembert's paradox. And the D'Alembert's paradox has given us the idea that it is not enough, or it is essential to study the viscous flow for a more general class of problem where the potential flow will fail. Again, the concept of the introduction of the circulation of strength, certain strength, finite strength, has talked about the lift force, and which this lift force which plays a very significant role when you look at a body is moving in a fluid, whether it is in water or it is in the air. And we have seen particularly it is more important when one thinks of the aerofoil theory or the hydrofoil theory, and that is why the results of Kuta and Chukovsky, which becomes more important, which provide, although it is based on the potential theory, it gives a good understanding about the lift force and the moment acting on the aerofoil or in a similar case the hydrofoil. So we have seen that, and all these are one aspect of the problem. We have just assumed here whatever I am talking about, we are talking about the flow, just assume that flow is incompressible and fluid is irrotational. So when it has come to the motion characteristics, all these days we have talked about inviscid fluid when it has come to calculation of force and the pressure. But in the next few classes, rather we will spend more how the Euler equation of motion or the Bernoulli's equation of motion for a potential flow associated with a potential flow will play a very significant role. This is another aspect of this and whatever we have talked with the understanding of the flow characteristics of irrotational motion for associated with incompressible fluid, and if we have assumed, we will assume further that the flow is inviscid, then we will go to the details of the free surface hydrodynamics flow, and that is lead to the theory of waterways. Before going to that, again let me talk about, because while talking about the flow characteristics and the flow on the boundary of the surface, we have emphasized what happens when we have a fluid, because I was just telling you about the boundary, because you may have a Laplace equation satisfied by the velocity potential or the stream function, but when we have any boundary, so there are couple of boundaries that always I talk of rigid boundary. We can talk of rigid boundary, which is, you can talk of a flexible boundary. Our boundary may be irregular, or we have singularity on the boundary. Then another aspect is that the boundary may be moving or fixed. Fixed or moving. For potential flow, we have also seen if the boundary is rigid, associated with rigid boundary, if the flow is, if the boundary surface is rigid and flow is a potential type, then we have del phi by del n is 0. On the other hand, if we have seen that if a boundary is moving, then we have seen del phi by del n equal to q dot u, q dot n hat. So, that means if this is the q is the speed at which the particle is moving or body is moving, and hat is the normal direction, then we have seen that this is also gives about on a moving boundary. Then again, but what has happened? There is another kind of boundary, that is the free surface boundary. So, what happened here when we think of a free surface boundary, particularly this comes when you analyze problems associated with this gives us a new class of problem when you look at. That is why I say that in the next few classes we will talk about free surface. The mainly broadly we will talk about free surface hydrodynamics. Basically, here when in this case what will happen, that means I have a surface which is free to the, here free surface means I always say that surface is free to the atmosphere. So, this surface is not a fixed surface, unlike you say bottom bed, bottom sea bed which is fixed. It can be also moving, because when there is movement of sediment at the bottom of the surface, the sea surface can also need not be a fixed one, fixed or moving. So, this is the, here the bottom bed can be also, because the when the unlike a case of a rigid fixed bottom bed or a rigid having a rigid bed. So, this surface also can be, there are so many questions comes, the surface need not be uniform, it can be of any shape. Then here we may have rigid bed, the bed may be porous, the bed may be rigid, the rest bed sometimes we, when the it comes to the bottom bed, sometimes we call it as a poroelastic bed, sometimes we generalize the sea bed as a viscoelastic bed. So, like that, but what happens when it comes to the free surface? The free surface, one of the things, if I say y is equal to eta is the free surface, and this free surface is not a known surface, the surface is not known, but what happens on the free surface? The pressure is always known. The pressure is known. So, that leads to a new class of problem, because there is a surface, the boundary of the surface is not known, and that although we solve in the fluid domain, we again assume very simple, we assume the flow is incompressible, we assume the fluid is inviscid. Even if under this irrotational motion, flow is the motion is irrotational, we have an inviscid fluid, inviscid incompressible. Even if under these assumptions we also we solve here the Laplace equation, but still the complexity comes, because on the free surface the boundary y is equal to eta itself is not known a priori, whereas the pressure is prescribed on this boundary. And in many situations also, if we say that this is a moving boundary, so we can also lead to a similar problem, that the bottom boundary need not be known a priori because of this. This leads, and again the surface boundary condition is, if we will come to the detail, we will see that the surface boundary condition, surface boundary becomes very highly nonlinear, and this nonlinearity on the free surface, that means here we will solve a Laplace equation, but as a potential flow problem, but our boundary condition become highly nonlinear. Another aspect which I would like to remind you here, that because the domain, because the surface, the Laplace equation is a linear equation, if the boundary conditions are linear or the boundary condition is smooth, there is no singularity, there is no nonlinearity on the boundary surface. Often superposition principle has helped us in superposing many solutions or many problems together, and then making the original problem a complex one and analyzing that problem in a suitable manner, which gives nice characteristics of the flow and which are more applied. So, here also when the problem becomes, because in the free surface hydrodynamics also we will see that there will be several aspects of the problem when a body is in the water, and once even if we linearize the whole problem, we will still able to get a good approximation to a very real life problem, and that approximation is possible because rather the problems will be highly applicable. It is because we will solve still a Laplace equation and under the assumption of the linearized conditions, because once the conditions are linearized, various characteristics can be coupled together, particularly superposed together. Various problems associated with the flow can be superposed together to get, like if I say that I have a body, or let us see the motion of a ship, anything which is moving in water, if the body is fixed, then that will give me a problem of a scattering problem, because when there is a water, it will come, that will be a incident potential, there will be a incident wave in the ocean, and there will be a reflected wave. But when this ship will be moving or the body will be oscillating, then we will have a radiated potential. So, in the process what will happen, then because superposition principle holds good, we can always find the total potential phi as a combination of the incident potential plus the scattered potential plus the radiated potential. This is not only in case of a ship, in many, when we have analyzed the flow characteristics in the presence of many such obstacles, we can always combine them together. The solutions which basically the superposition principle will hold good, and that will help us in solving many problems in this. Another aspect of this free surface hydrodynamics problem is that this leads to the free surface hydrodynamics, because we always comes across a free surface which is nothing but a wavy surface, and this will lead to the generation of waves, and what we say, we call this will lead to an area what is called the area of water waves. In fact, among all those waves, electromagnetic wave, we have seen electromagnetic wave, we see flexural waves, particularly when you have solid, we have seen tensile membrane, on a membrane there is a wave propagate, string there is a wave propagate, we have quantum mechanics, we have particularly in electromagnetic waves. But here, out of all these waves, water waves is the most unique, because here what happened in the while analyzing problems related to waterway, often we come across problems which are in the unbounded domain, and when we look at problems in the unbounded domain, particularly we have to specify the radiation condition or the far field condition. We have seen in our previous analysis that when used to analyze the flow past a cylinder, we have always analyzed that as if the flow is uniform along the horizontal, flow is uniform along x axis. Also there are, we have also analyzed when the fluid is at rest at infinity. We have already talked about fluid is at rest at infinity. So that means when I have to analyze a flow in a unbounded domain, that means domain which is infinitely extended, or unbounded, then I have to describe some kind of behavior of the flow behavior at infinity, at the far field. In fact, that leads to, because we have seen in case of the radiation or full radiation current problem, Sommerfeld radiation condition, so this has taught us that when we have the, even if we solve sometimes Laplace equation, and particularly for waterways, we, this radiation condition gives a type of wave which is not known at the far field, and then this adds another complexity to the problem, because the far field behavior is not known a priori. Like the free surface, the surface, boundary surface on the water surface is not known a priori. Similarly, here the far field conditions are not known a priori. In fact, those far field conditions often gives us information about the nature of the kind of problem we are dealing with, because like if you look at the scattering of a wave by a breakwater or a barrier, then the far field behavior will give us the reflection and transmission coefficients, and that talks about the nature of the obstacle, the reflective characteristics or the dissipative characteristics of those structures. So often we need to know, in the process of obtaining the solution, we need to understand the physical phenomena that is associated with it. Again, there are structures which we will look into, where we will look at the boundary surface, where the boundary is flexible in nature, flexible boundary. Unlike the case of rigid boundary, the problems is not as easy when we think of a flexible boundary. In case of a flexible boundary, we have seen that today this is another area which has come up, that is the area of hydroelectricity. It is a mutual interaction of this is basically the area of the mutual interaction of the hydrodynamic and the elastic forces, and that has led to a area, and there one has to, almost every problem one has to consider, that is as if the hydrodynamic forces are interacting with a elastic forces, and there which is of recent interest, and many problems which are being earlier handled under the assumptions of the body as a rigid body has to be generalized. Many theories are being generalized under the assumption, because today we are looking into structures which are very large in nature, because of the largeness of the structure, we assume that the body, rigid body analysis is not very helpful, whereas the flexibility has to be taken into account in the process. Hydroelastic analysis is becoming much more important. Again, I will talk to you another aspect of the problem, that is basically when it comes to the free surface wave problem. There are several okay, apart from the linearity, what will happen if we have the non-linear boundary conditions? When you have the nonlinear boundary condition, that means the free surface condition is nonlinear and we do not linearize the problem, then very few problems which has been we are able to get solution. And in fact, today a major part of the analysis associated with waterways are based on the linear theory, where we find several applications. But when it comes to nonlinear waterway theory, the theory is very vast, and in almost all the cases efforts have been made to assume that the problem is linear in nature, to linearize the problem. And in the process there are several theories. We will come to all this. We have started with Airy's wave theory, Airy's wave, then we talk about Stokes finite amplitude wave, we have conodal wave theory, we have string function theory, then we have solitary wave theory, and many more. Out of the Stokes finite amplitude wave theory, the first order wave theory is sometimes same as the Airy's wave. So, with this understanding, in the coming series of lectures, we will go in detail to talk about water waves. Basically, we will introduce the theory of water waves, and when it comes to the theory of water waves, there will major emphasis will give, and once major emphasis will give on the linearized theory. And the moment we had a fluid flow, and then in the process we are bringing another phenomena associated with the wave. So, the two things, the wave theory and along with the fluid flow, makes the problem more complex. Like you look at, let us look at the problem in a river, flow pattern in a river. When you look at the flow pattern in a river, we always look at as if the mass is moving, water particles are moving because from one end to another. But in the case of when we have look at the same wave in the ocean, here we have two things. We have the more important is the wave, apart from, because here the wave part is negligible when you have a running wave in a we are talking about the water flowing in a channel, a canal, or even if the river. But in the case of their major analysis, the civil engineering aspect, hydraulic analysis is done assuming free surface impact is negligible. On the other hand, in the case of in hydrodynamical analysis, particularly when we look at the ocean in water, or we always give much emphasis on the aspect of wave, and this wave. So, the description or the understanding of the physical characteristics of the wave along with the flow description makes the problem more complex, and there are many branches of marine hydrodynamics or rather ocean engineering which gets benefited because of this analysis. If you look at the areas like ship hydrodynamics, where the seakeeping and maneuvering of vessels, and particularly when you look at the courses, look at calculating the wave resistance on a vessel or any other moving body, or even if you look at calculating the wave load on a offshore structure, or understanding the how the wave structure interact in case of a large floating body. All these things, one has to not only understand the wave characteristics, one has to understand the characteristics of the structure itself, and along with the characteristics of the flow pattern. So, because simple problems which when put together has given to gives rise to solution to a large class of problem which are of applied in nature or of large importance to various industrial application. So, with this understanding, again I will say when it comes to, I will just highlight a little more about modeling, because next class we will come to the details and talk about modeling. When I talk about modeling, particularly today we see there are several wave models or physical models rather. When it is physical model, but here there are two aspects. One is a physical realization. We always call it give a mathematical model to a problem. Then we have experimental model testing is done, experimental models. So, what we always do a numerical, often we say numerical models. And then sometimes you have, so when one has to say that a real more accurate realization of a model, because then we have observational data analysis. Observational data analysis. So, a model, physical model or a model, we say that this is the most appropriate when the experimental model, the numerical model and the observational data, they all gives rather the three results associated with these models the coincide. Then we say this is one of the most well known physical model, or that gives a more accurate realization of the problem. But often it is very easy. Sometimes people say there are, although there are debates, I will not go to those debates. Sometimes people say that it is easy to make a mathematical model, or sometimes people say it is very easy to make a experimental model, although there is a large debate on this. But always doing an experimental model is a difficult one of a problem, because you have to develop a prototype, and for large many problems today, because of the availability of the high speed computer, you can always make a mathematical model and accordingly get a corresponding numerical model, and this numerical model, if we can validate with observational data, then several observational data, then we feel that our model is a more accurate one. There is, although there is a good amount of analysis associated with this numerical model, because when you have a model, you always look at numerical model or numerical, you always look into the convergence test of the solution. Convergence of the solution associated with the model, and then when you look at the convergence of the solution, you also look at the uniqueness, unique characteristics. But in many real life problem today, like if you look at many oceanographic problems, there are observational data analyzed and then numerical models are developed, where they go on testing from one result to another, and then but because of the complexity of the problem, often it is very difficult to do this kind of analysis, the convergence analysis or the uniqueness analysis, but still several methods are adapted which gives a better realization of the problem at hand. And another aspect is that experimental model. Experimental models are always not possible for all class of problem, because it is not only physically, many times it is impossible to do experimental models for. Like today, if I look at the wave breaking phenomena, it becomes highly, there are various explicit formulas which are there in the literature to understand this wave breaking phenomena. After a lot of model test people have done, but still we are not getting that what exactly is happening when a wave breaks near the shoreline. So, anyway, all these things will comes as a part of a physical model, but one has to will try in a physical model to, if the three things we can do, a mathematical modeling, the numerical simulation of the model, and then experimental verification along with observational data analysis. All these 3 or 4 things together give a more accurate realization of a physical problem, but and there should be a proper, if one has a very good understanding about all these 4 aspects of the study, then it will be very easy for him to say whether a model is a more accurate or not, because often we are not able to analyze the convergence of the solution of a large number of problems. Anyway, with this background, in the next class we will talk about introduction, we will talk about waves, basically the water waves. We will develop the theory of water waves and then try to work out few simple problems on the waves and try to understand how various types of wave, what are the various types of wave exist, and what are the, how they are classified, how the theories are developed, and then try to analyze some of the simple wave problems that we come across in our day to day life, and which are of also interest to the marine technology or marine industry. With this background on waves and with the summarizing all, just a small review of what all we have been studied in the last series of lectures, I will stop here. Thank you very much.